Number 1, first, the sample space. If you have a deck of cards, no jokers, your sample space is 52. There's 52 totals. 52 total cards. The hearts and diamonds are red cards. The spade and clubs are black cards. So, the probability of a queen. There are 4 queens out of a total of 52 cards. So 4 out of 52. Reduced, that is 1/13. Probability of a club. Clubs are all these cards. You might see that that's a quarter of the cards altogether, or you could start with the fact that there are 13 clubs out of a total of 52 cards. Reduce that for 1/4, 1/4. You need to have your answers in reduced fraction form here in order to get credit. The queen of clubs. There's just one queen of clubs. So there's one choice there out of 52. Probability of a 3 or an 8. 3, getting a 3 and getting an 8 are mutually exclusive events. They cannot happen at the same time. So, or we can just add these together. The probability of getting a 3 is 4 out of 52, plus the probability of getting an 8 is 4 out of 52. So we can add those together to get a probability of 8 out of 52. And reduce that and you get 2/13. Probability of a 6 or a spade. Here's the 6s. Here's the spades. These are not mutually exclusive. There's overlap. You can see that that 6 of spades is the overlap. So you can just count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 of them. Or for mutually exclusive, you can take the probability that it was a 6 and add that to the probability that you had a spade, and then subtract off the overlap. That's for events that are not mutually exclusive, so the probability that you have a 6 and a spade. So the probability that you have a 6, that's 4 out of 52, plus the probability that you have a spade, there's 13 of those, so 4 6s, 13 spades, and then subtract off the one that you just double counted, that 6 of spades. There's one choice there. So 4 plus 13 minus 1, that'll give us 16 out of 52. Reduced becomes 4/13. F, probability that you have a 6 and a spade. So that something is both a 6 and a spade. There's only one choice there. So 1 out of 52. Now you might ask, well, Jana, I thought when you said and, you should multiply. So I should take 4 6s and times that by 13 spades, and that should be my answer. Well, no, that would be if you were drawing 2 cards. If you had a 6 and then a spade. But we're just doing 1 card. We just want the 6 of spades, which is just one choice, one way to get that, 1 out of 52. Similarly, a black king. Okay, how many black kings are there? Well, the black cards are the spades and the clubs. So there are 2 choices for black kings. So that would be 2 out of 52, which reduces to 1/26. Similarly, red and a 7. Which cards are both red and 7? The red cards are the hearts and the diamonds. And so there are 2 red 7s. So again, that will be 2 out of 52 or 1 out of 26 reduced. A diamond or a heart. Diamond or a heart, those are mutually exclusive events. You can't be both a diamond and a heart at the same time. So you can, in that case, you can take the probability that it's a diamond and add the probability that it's a heart. So you've got 13 out of 52 diamonds and 13 out of 52 hearts, which gives you 26 out of 52 or 1/2. And you might have just jumped right to the 1/2. Diamond or heart, that's half the cards. Probability of getting a black card, 1/2. Half the cards are black, half are red. 2A, find the probability that your state starts with an M. I just Googled a list of states and counted them. I found 8 that started with an M out of a total of 50 states. So my sample space is 50. That will be the denominator in all of our problems. So 8 out of 50 or 4 out of 25 would be your reduced answer. You must reduce your fractions to get credit. B, find the probability that they don't start with a vowel. Well, I just counted the probability that they started with a vowel. It was a smaller number. 12 out of 50 started with a vowel. So to find the probability of the complement of that, again, complement means not this probability. So the probability that they started with a vowel was 12 out of 50. Its complement will be the ones that didn't, so the other ones. A complement is 1 minus the original probability. So in our case, that would be 1 minus 12/50ths, or 38/50ths, which reduces to 19/25ths. Now you could also just have counted up all the states that didn't start with vowels, gotten 38, and gone directly to this step. But I wanted to show you, again, how the complement works. Number 3, probability of getting a 7 or an 11. So these are mutually exclusive. Since these are mutually exclusive, they can't happen at the same time. We can just find the probability of getting a 7 and add it to the probability of getting an 11th, and we'll have our answer. So here's the sample space for dice. What is the size of our sample space? How many choices are there here for rolling 2 dice? 36 total choices. So how many of them result in getting a sum of 7? They kind of follow this diagonal. And how many choices for getting an 11? These 2 choices. Count them up. 2, 4, 6, 8. So there's a total of 8. 8 out of 36. 2 9s. Next problem, problem 40. The first thing we need to figure out is our sample space. If you spin that spinner in the book twice, what are the possible things that can happen? We're going to need to make a sample space kind of like the one that we found in the previous problem. You could get a 0 and a 0. You could get a 0 and a 1. You could get a 0 and then a 2. You could get a 1 and a 0. You could get a 1 and a 1, a 1 and a 2. I'm going to just keep filling out this sample space. So here I will try to do part A I want an odd number on the first spin and an even number on the second spin. Well, an odd number on the first spin, that's going to be this row and this row. And then I want an even number on the second spin. So that'll be even, 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 even. So there are 6 choices that fall into that category. So what is my sample space? I never did count up how many items in my sample space. Let's see. I've got 5 by 5, so that's 25 items in my sample space. 25 choices for how these 2 spins could go. So I know that an odd number first and an even number second happens 6 times out of these 25. So 6 25ths. Next, a sum greater than 4. Well, so greater than 4, that means 5 or more. So let's see, these have a sum of 5, these have a sum of 6, these have a sum of 7, this has a sum of 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of 25. Reduced is 1/5. Reduced is 2/5. You must reduce the fractions or you won't be given credit. Part C, even numbers on both spins. None in this row because those both all have an odd number in the first spin. So even numbers, both spins. Nine total. Out of our sample space size was again 25, so that's 9 25ths. A sum that is odd. Well, 0 plus 0, not odd. There's 0, sum of 1, a sum of 3, a sum of 5. I'm circling all the numbers that when I add them up, so like this one, 2 plus 1 is 3. 3 is odd, so that counts. Like this one, 2 plus 4 is 6. That's not odd, so that doesn't count. You see a pattern after a while. Count those up. There are 12 of them. 12 25ths. And lastly, part E, the same number on both spins. 1, 2, 3, 4, 5. This happens 5 times. So 5 out of a total, our sample space is 25. So that's 1/5. Again, the number in your numerator is how many times it happens. The number in your denominator is the number of items in your sample space. Determine whether these events are mutually exclusive. Mutually exclusive means they can't happen at the same time. There's no overlap. Or if you drew them with a Venn diagram, there would be one event, there would be the other. They do not overlap at all. They don't happen at the same time ever. So part A, getting an even number and getting a number less than 3. Those could happen at the same time. 2 is less than 3, and 2 is an even number. So no, that is not mutually exclusive. B, roll a die. Get a prime number, get an odd number. Well, 3 and 5 are both primes, and 3 and 5 are both odd, so those could happen at the same time. So that's not mutually exclusive. C, roll a die. Get a number greater than 3, get a number less than 3. Those things never happen at the same time. That is mutually exclusive. D, select a student in your class. The student has blonde hair, the student has blue eyes. Could that overlap? Yeah, you could have somebody who's blonde and blue-eyed, so no, that's not mutually exclusive. Mutually exclusive is this picture. They could never happen at the same time, separate events. E, select a student in your college. The student is a sophomore, the student is a business major. Could those things both happen at the same time? Yes. So that is not mutually exclusive. F, select any course. It is calculus and it is English. That is mutually exclusive. can't have both of those things happen at the same time. G, registered voter. The voter is a Republican, the voter is a Democrat. Those are mutually exclusive. They don't overlap. You're either a Republican or you're a Democrat. Number 6, I started with showing you the sample space for cards. Let's talk about what is the sample space. The size of the sample space is 52. In cards, there's 52 total cards, a 4 or a diamond. So the first thing we need to figure out, 4 or a diamond, do those overlap? Yes, they do. So those are not mutually exclusive. So when something's not mutually exclusive, we need to use this formula. You take the probability that you get a 4 and add it to the probability that you get a diamond, and then subtract off the overlap. Subtract off the things you counted twice. So things that are 4 and a diamond. So the probability that you are a 4. Four out of 52, plus the probability that you're a diamond, 13 out of 52. Subtract off the thing that you counted twice, the 4 diamonds. So 4 plus 13 minus 1, that's 16 out of 52, which reduces to 4/13. Now let's take a look at this. If you just circled these, the 4s and the diamonds, and just count everything that's in that group. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That brings you right here, 16 out of 52. So you can do the problem without the formula if you just count up the things that are 4s or diamonds. Next, the probability that you will get a club or a diamond. Okay, so the clubs, those are here. The diamonds, those are here. Looks like half to me. I'm going to go right down to the end and put 1/2. But I want to show you how that works with the formulas. If things are mutually exclusive, if there is no overlap, you can just take the probability of a club and add it to the probability of a diamond. See how this matches up? You can skip this part here. You can skip subtracting off the overlap. You can just add the two together. So kind of the long way around this, the probability of getting a club, that's 13 out of 52. Plus the probability of getting a diamond, 13 out of 52, is equal to 26 out of 52, which, like we thought, adds up to be 1/2. But I wanted you to see how the formula worked there as well. Probability of getting a jack or a black. Again, not mutually exclusive. Since it's not mutually exclusive, you'll add the two probabilities. The probability of being a jack, that's this group, plus the probability of being a black card, that's this group of cards. And then you'll have to subtract off the overlap. Subtract off the things that just got counted twice when you added them up. So the probability of being a jack, that's 4 out of 52, plus the probability of being a black card, that's 26 out of 52. You could put 1/2 here if you wanted to. And then subtract off the overlap. 2 cards got counted twice. That's 28 out of 52, which reduces to 7/13. Now again, you could do this without the formula. You could just count these up. Okay, I've got 26, 27, 28. 28 cards out of 52 fall into this category, 7, 13. So you can kind of skip ahead to this point, but I wanted you to see how that formula works. I have a copy of my table. The first thing that I do when I do this problem is figure out my totals. Figure out how many total first-class letters there are by adding these. Figure out how many ads I have by adding these. How many magazines. And then how many were delivered to a home, add up the first row. How many were delivered to a business, add up the second row. And then I should be able to here find my sample space. How many total pieces of mail did I have? Either by adding up my home and my business, or adding up the first class, the ads, and the magazines. Should give me the same number. This number right here is the number of items in my sample space. First problem, A, the probability that I went to a home. Well, how many went to a home? Well, let's see. The total that went to a home was 934. So that's 934 out of my total sample space of 2784. You can write that as a reduced fraction. Or a decimal. An ad or a business. Well, ad or a business, let's see. So that's ads right here, or business right here. So if I just add up those four numbers, that'll tell me how many went to an ad or a business out of 2784, or you could use your formula. These are not mutually exclusive, there's overlap. So if we take the probability that you're an ad, 1427, plus the probability that you're a business, went to a business, 1850, and subtract off the overlap. There's the overlap, 1021. All out of our total number of sample space, which was 2784. You get 2256 out of 2784, which reduces to 47/58, or 0.81. Next, first class letter or home. So here's the first class letters, and here's the home. You see, not mutually exclusive. So we have to add up the first class letters, 1057, plus the homes, 934, and then subtract off the things that we counted twice, the 325. Over our total. And that will give us 1666 out of 2784. Or a reduced fraction of 833 out of 1392, or 0.598. First off, we have to figure out our sample size. How many patients were there? So to do that, you add up your total number of patients there, you should get 30. So our sample size is going to be 30. Part A, The patient had exactly 2 tests done. You look and you see that 2 patients had 2 tests done. So that's 2 out of 30, or reduced to 1/15. Part B, at least 2 tests. At least 2 tests means 2 or more. 2, 3, or 4 tests. So you just add them up. 2 people had 2 tests, 3 people had 3 tests, and 5 people had 4 tests. That's 10 out of the 30 people, which is 1/3. C, at most 3 tests. So at most 3 tests means that you had 0 tests, or 1 test, or 2 tests, or 3 tests. At most 3 means 3 or less. So add up the amount of people that had that. 12 had no tests, 8 had 1 test, 2 had 2 tests, and 3 had 3 tests. Out of a total of 30. Which reduces to 5/6. Part D is tricky because 3 or fewer, that's actually just what you did there. So at most 3, and 3 or fewer both mean 0, 1, 2, or 3 tests. So that probability is going to be the same exact problem, 5/6. Number 9, 2 dice are rolled. That automatically brings to mind this picture from your formula sheet. It shows you the possibilities for when 2 dice are rolled. You could get a 3 and then a 2. You get a 2 and then a 3, and so on. It lists them all. So first off, sample space. How big is this? How many choices are there? There are 36 choices here, so all my probabilities are going to be out of 36. So first off, a sum of 8, 9, or 10. Where is that? Okay, 8. It's here. All the sums are in a diagonal. Or 9, or 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of my sample space of 36, which reduces to 1/3. Doubles or a sum of 7. Here's my doubles. Now, what I would be concerned about here would be if there was any overlap at all, if these were not mutually exclusive. But it turns out that they are mutually exclusive. They never happen at the same time. You don't have a double and a sum of 7. So you're just looking at that subset of your sample space. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 of them. So 12 out of 36. Or again, 1/3. Next, a sum greater than 9 or less than 4. Well, greater than 9, that's a sum of 10 or more, that's these. And less than 4, so that's 3 or less. So that's these. These are mutually exclusive. There's no overlap. They don't happen at the same time, so I just count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 36, which reduces to 1/4. Which is the least likely to occur? Part C, 1/4 is the smallest fraction there. 3 dice are rolled. Find the probability of getting triples. Before we start this, I want to talk about sample space. You notice that I included the rolling 2 dice sample space. There are 36 items here. Now imagine that you did another roll of the dice after this. You'd have to multiply this by 6. You'd have to do this picture over 6 times. One with 1s for the 3rd roll, one with 2s for the 3rd roll, and so on. So your sample space actually ends up being 6 times 6 times 6 is 216. There are 216 ways to roll 3 dice. So part A, getting triples. How many triples can you get? Well, you can get all 1s, all 2s, all 3s, and so on. There are 6 ways to get all triples. So that's 6 out of 216, or 1/36. Part B, a sum of 5. Now this is a little trickier. I just try to list all the ways I could possibly get a 5. I could get a 1, and a 3. That would make 5. I could switch the order around on that. So I could get a 1, 3, 1, and a 3, 1, 1. How else could I do it? I could get a 1, a 2, and a 2. Or I could get that 1 in a different position. And I think that's it. That's all the choices, because if I try to put a 4 in there, a 4, the least I can do is a 4, a 1, and a 1, and that gives me 6, too big. So I think those are the only ways that I could get a sum of 5. So that's 6 out of a total of 216, which is 1/36. A little bit tricky.